We will be discussing why the boiling points of branched chain alkanes are lower than the boiling points of straight chain alkanes. Firstly, what is a boiling point? A boiling point is the point in which the vapor pressure of a substance is equal to the pressure applied from the substance's environment measured in units of temperature. What is vapor pressure, you might ask? Vapor pressure is the tendency of a substance to transition into its gaseous state. The vapor pressure and boiling point of a substance are inversely proportional to one another. What does this mean? In order to conceptualize this, let's use a real-world example. A student who is highly motivated to study will find it much easier to begin studying, whereas a student who dislikes studying will find it difficult to begin studying. We can apply the same concept in chemistry. A substance with a high vapor pressure will have a great desire to transition from liquid state to vapor, and resultantly, the substance will find it easy to meet its boiling point, and vice versa. Vapor pressure of a substance is affected by multiple factors, which include the surface area which the substance assumes, the temperature of the substance, and the intermolecular forces present between the molecules of the substance. We must understand the relation between vapor pressure and intermolecular forces to discover why the boiling point of branched chain alkanes is lower than the boiling point of straight chain alkanes. Intermolecular forces are weak forces of attraction or repulsion that exist between molecules, hence the prefix inter. A substance's vapor pressure and intermolecular force strength are inversely proportional to one another. By applying the same relation we discussed previously, we know that the higher a substance's vapor pressure, the weaker the intermolecular forces of a substance must be, and vice versa. How can we apply our knowledge about boiling points, vapor pressure, and intermolecular forces to justify the boiling points of alkanes? We know that branched chain alkanes have lower boiling points than straight chain alkanes. But why? Let's explore these relationships deeper with alkanes. The arrangement of this pentane alkane is considered to be a straight chain. If we introduce a second pentane alkane, we see that intermolecular forces form between the alkanes. Specifically, van der Waals forces. Van der Waals forces arise from momentary dipoles as a result from the random motion of electrons on atoms within molecules. The straight chain alkanes are stacked, and intermolecular forces that exist are considerably strong due to how close the interacting molecules are. The arrangement of this pentane alkane, also known as isopentane, is considered to be a branched chain. If we introduce a second isopentane alkane, we see that the van der Waals forces that exist in straight chain alkanes also form in branched chain alkanes. And what is the difference that causes the change in boiling points among the two? What sets the two apart is the distance in which the intermolecular forces exist. The intermolecular forces that are much closer are in the straight chain example, and they are much farther in the branched chain example. The relation between the intermolecular force strength and the distance in which the force is applied is also an inverse proportionality. As the distance in which a force is applied increases, the strength of the force proportionally decreases, and vice versa. How does all this connect to alkane's boiling point then? We can relate all the proportionalities and determine that the greater the distance and intermolecular forces applied, the lower the boiling point of that substance, and vice versa. Since branched chain alkanes intermolecular forces exist over a greater distance, we can derive that the boiling point of branched chain alkanes must be lower. An easy way to remember this relationship is by thinking about the game Tetris. Long linear shapes are good for increasing combo potential since they stack well. Complex geometric shapes, on the other hand, decrease the chances for comboing since they do not stack well. Treat the long linear shapes as straight chain alkanes and complex geometric shapes as branched chain alkanes, and their ability to create combos as the boiling point. The greater the combo potential, the greater the boiling point.